Welcome back to our series on probability theory. I'm Mark Ledbetter, and this is lecture video 13, and we're going to talk about mathematical expectation, and this is part 2. Last time, we defined the expectation of a random variable x, which is the sum of x times f of x over all of the values of x in its space. And if we want to take the expectation of a function of x, let's say u of x, then we replace x here with what we're taking the expectation of. So x here becomes u of x, then times f of x, x in s. So now, today, we want to go over some properties of expectation. I'm going to try to get us into the geometric distribution. We'll see how far. So let's talk about a theorem that's very important, and these are properties of expectation here. And the key word here is when the expectation exists. Expectation does not have to exist. We will see some distributions this semester where it does not. Certain expectations do not exist. So we're going to define constant c, c1, c2, and then we're going to define functions u, u1, and u2. First off, the expectation of a constant is just its constant. Remember, the expectation multiplies by a probability distribution. So if it's constant, there is no probability really associated with it. It's constant. So the expectation of a constant comes back as a constant. That makes sense. And then we're going to say that the expectation of a constant times a function, u of x, well, we can pull the constant outside of the expectation. So we have c times the expectation of u of x. And then if we have a linear combination, c1 times u1 of x plus c2 times u2 of x, well, we have a plus here. And so we can break it up into two expectations, and using the property 2 above, we can pull out c1 and c2 here, okay? And then we have the linear operator. It's a linear operator, so here we have a line, the expectation of a line, but a random line, a times x plus b, where x is a random variable. And using the above properties, we can see that a times e of x plus b, where a and b are constants. And then here we've got a quadratic, and the expectation of it, everywhere there's a plus, we can just break it out. And here, a, b, and c are constants. So let's prove number 1. The expectation of a constant is a constant. How we do this is we simply use the definition of expectation. So e of c is equal to the sum of what is inside the parentheses c times f of x. So this means that we would have c times f of 1 plus c times f of 2 plus all the way up to c times f of m. Or if it's infinity, it would just keep going. So here, I showed the same thing, but for 3x. And you notice that here, you have c in everything. And here I used the number 3. So 3 is in all these terms. And so I can factor 3 out of every one of the terms. And when I pull 3 out to the front, then I'm left with what's in the parentheses in this case. So 1 plus 2 plus 3 plus 4. Okay? So that is why we can factor the c in front of the summation, because it's in every term. Okay? And so remember that the sum of a PMF over all the values of x in the space is simply 1. And so, because it's a probability distribution, so we have c times 1, which is c, and we've proved it. So the proof of 2, again, we start with the definition, c times u of x times f of x. The c can come out because we've already shown that in the previous. And then what we have left here is simply the expectation of u of x. And the proof of 3 is very similar. So I'll let you walk through that, but it's very, very similar. Okay. And the proof of 4 and 5 will probably be homework. Okay, so there are some tricks to that, or details, not tricks. So the expectation E is called a linear operator or a distributive operator. As you see, we could distribute it across addition. We can also distribute it across subtraction. So let's do another example. Let u of x be x minus b squared, where b is not a function of x. So we're not saying that b is a constant, but we are saying that it doesn't have x. It's not a function of x. So let's say that this exists. The expectation of x minus b squared exists. We want to find the value of b which minimizes this quantity. So what we do is we're going to say let g of b equal e of x minus b squared. Now we simply square the x minus b inside the expectation. So we end up with x squared minus 2bx plus b squared. And from our properties above, our theorem above, we know that this is equal to e times x squared minus 2b times e of x plus e of b squared. And this turns out to be, since it doesn't have x in it, it's like a constant with respect to x at least, becomes b squared. So we have this. So we have e of x squared minus 2b e of x plus b squared. All right. And what we're going to do is we're going to take the derivative of g with respect to b, or with respect to x. So we're left with, with respect to b, that's right, because this is a function of b. So we have, here we'd have 0, and then here we'd have negative 2, e of x, and then plus 2b. And so to make the derivative either a maximum or a minimum, we set it equal to 0. And so we can solve for b now, and we'll have 2b is equal to 2e of x, which gives us that b is equal to e of x after we cancel 2 on each side. And you could check the second derivative to see that it is, in fact, let's do that. The second derivative with respect to b is going to be 2, because here we don't have a b, and here we do. And this is greater than 0, so therefore g of b is concave up. So b is b equals e of x is a minimum. So review your calculus. If that's not, a maximum is concave up. So let's see, minimize. Yeah, this is a minimum. Yes, exactly. So I was right. I wrote it down on my other notes incorrectly, but it is a minimum. So there you go. That's the answer there. Now let's look at something called the geometric distribution. Now the way we're going to do this is we're basically going to derive this, and so we're not going to have all the things that we should have with a distribution when we finish in this section. We need the mean and the variance and some moment generating functions and some other things that we'll get later. So we're going to let S, that's not a 5, that's supposed to be S, be the sample space of an experiment, and let P be the probability of success. I want to point out that P is in the interval of 0 to 1, but P is not equal to 0 and it's not equal to 1. Okay? That's actually very important in some of the proofs. We're going to let Q be 1 minus P, and that's the probability of failure. Now, in the real life, P is whatever we're studying. So if we were studying a death, obviously we wouldn't think of that as success, and we wouldn't think of life as a failure. But this is the terminology that's used. So don't let that technical or reality get in the way of this technical definition, which apparently wasn't thought through very well. Okay, so let's assume that each trial is independent of every other trial. We're going to repeat the trials until the first success occurs. We're going to let the random variable x denote the number of trials until the first success occurs. It's very important to define x, your random variable. So the space of x, s of x, is going to be 1. We can't have a success unless we perform the trial at least once. But it doesn't have to be a success on the first time or the second time or the third time. Those are all possibilities. But we can go on, technically, in theory, we could go on forever. Okay. So this is a example of an infinite but countable space for x. It's still discrete. So we want to know what's the probability that the random variable x is equal to some specific value x in its space. So we're going to say that there must be x minus 1 failures before the first success. And this means success, before the first success. And then we'll have 1 success. Okay? So when we look at this, the probability, we have Q is the probability of failure. So Q, and there's going to be x minus 1 of those, and then 1p. So we've got Q to the x minus 1 times p for all x in S, and x starts out at 1 on so forth. So P and Q are greater than 0, and because of this, this is a PMF. Now we need to show that this really is a PMF. In other words, we have to show that f of x, the sum of f of x, across all x in S, that has to be 1. Now, notice that Q has an exponent of x, but P doesn't. So I can again pull P out to the front of this summation. So now I just have Q. And if I write out Q of raised to the x minus 1, then, and I'm starting at x equals 1, right, up to infinity, then I plug in 1, and I get 1 minus 1 is 0. So Q to the 0 is 1. And then it goes up, Q to the 1, Q to the 2, Q to the 3, etc. If you remember, this is a geometric series, so this portion here is equal to 1 over 1 minus Q. Okay? So it's 1 over 1 minus this number. And we have P out in front of it. So P over 1 minus Q. Well, 1 minus Q is P, so here we have that it adds up to 1, which is what it's supposed to do. I have a proof here. We'll start there in the next video. Now, again, remember, please scan and upload your lecture notes before midnight of the date listed in the course calendar. They're for you, so make them neat. Update your formula sheet and update any definitions, theorems, corollaries, remarks that are helpful. We've gone over one of those in this, so you want to do that. If you have any questions, please visit my virtual office hours. If you can't make it to there, email me. I'm happy to help you. Until next time.